All right, now let's get started on the chemical bonds. Okay, so yeah, I'm still sharing the screen. All right, here we go. Covalent bonds. These are the ones we deal with the most probably when we're talking about biological molecules. So these and hydrogen bonds you're going to see a lot of. So you definitely want to focus on really understanding these two. So what is a covalent bond? Covalent just means that the electrons are shared between two atoms. So only the electrons in the outermost shell, again, those are the only ones we're really ever concerned with. So sharing of electrons in the outer shell is a covalent bond. It's really hard to break. The sharing is very strong, I guess. They're good sharers. So it usually requires some kind of enzyme, which is, we'll get into enzymes in a little bit, but those are proteins that help kind of speed up some reactions. So really hard to break. They're really strong, and they involve sharing of electrons. Those are the main take-home messages of covalent bonds. So for instance, if we look down here at these two hydrogen atoms on the left, remember hydrogen atoms each only have one electron, and they only have one energy shell. So they really only need one more electron to fill that first energy shell. So they often, very often bond with each other because they can each share one of theirs. So now, as you can see here, when they're bonded, both of them technically have two electrons, even though they're both being shared. So a hydrogen molecule, hydrogen gas is H2. So if there's two hydrogen atoms near each other, they're likely going to bond because it's an easy way to fill their valence shell. So that is a simple example of a covalent bond. And covalent bonds get a little bit more complicated because there's technically two sort of subtypes. You have polar and nonpolar. And these two really, the difference between them is whether the electrons that are shared, so if you imagine those two hydrogen atoms, if those electrons are shared equally, so one atom isn't pulling on the electrons, the shared electrons more than the other, that's nonpolar. The electrons are shared equally in a nonpolar covalent bond. In a polar covalent bond, they are not. Electrons are unequally shared. I think of that as one atom being greedier for the electrons than the other. So up here we have carbon on top. So this would be, I can't really see it. Okay, there we go. Two carbons bonding together. Neither of them is going to be greedier for electrons than the other because they're both carbon atoms. And I'm not going to get into what makes, I don't think I am, what makes one atom greedier for electrons than another. So don't worry about that. But if they're the same atom, they have the same pull on the electrons, basically. So like H2, anything with two carbons bonded, they're pulling on those electrons equally because they're the same atom. So two of the same atom are going to be nonpolar. When we look at oxygen, oxygen actually is very greedy for electrons. It loves holding the electrons closer to it than pretty much anything else it bonds with. So here we see hydrogen on the other side. And when an oxygen and a hydrogen bond together in a covalent bond, the oxygen actually pulls those shared electrons, so the electrons that hydrogen is sharing with it, it pulls the electrons closer to the oxygen. So because electrons are negatively charged and those electrons are a little bit closer to the oxygen, that means the oxygen is slightly negatively charged, which is that weird symbol you see in the bottom left of that diagram. Just don't worry about the weird delta symbol there. It's that negative is what you want to focus on. It just means it's partially negatively charged. So we don't consider it a full-on negative charge like we would with an ionic bond, which I'll talk about in a minute, but it's slightly negative. So the oxygen is slightly negative, and then the hydrogen is going to be slightly positive because the electrons aren't as close to it. So polar and nonpolar are very, very important concepts to understand when it comes to biological molecules, as well as water. And I'll talk about water in detail here in a little bit. Okay, so that's polar and nonpolar covalent bonds. Moving on to the next category, the broad category, ionic bonds. Electrons are not shared as they are in covalent bonds. Rather, they're transferred from one atom to another. So it's a complete transfer of an electron rather than a happy sharing between the two. So when these electrons are donated or accepted from one atom to another, this is called ionization. So an atom is ionized when it either donates an electron or accepts an electron. And these are always paired. If an atom is donating an electron, something else has to accept it, right? So the donator is called the cation, and the acceptor is called the anion. So NaCl is a great example. I'll use that down here in this diagram as our example. So NaCl is table salt, a very common ionic compound. So let's think about the valence shells here. So if you look at Na in its outer shell, it only has one little electron, and it wants 8, right? So it wants 8 out here, but it only has 1. Getting 7 electrons is going to be a whole lot of work for sodium. It's a lot easier for sodium to just get rid of that electron. Then that outer shell gets erased. And now its new outer shell, that second shell, is full. It has 8 electrons in it. So sodium wants to get rid of that outermost electron. So it becomes a cation and donates the electron, often to chlorine, Cl, which if you count up the electrons here in the outermost shell, you have 1, 2, 3, 4, 5, 6, 7. So chlorine only needs 1 electron. That's pretty convenient. So it will very readily accept that 1 electron from sodium. And because sodium is losing an electron is negatively charged, that means sodium is now slightly positively charged. So that's why it's the cation. And then chlorine, because it took on more negative charge by taking on that electron, it's now negatively charged. So you have Na plus and Cl minus. These bonds can usually easily be broken by water. So, salt will dissolve very easily in water, or relatively easily. I don't think I'm going to go into the details. I can't remember what I have on the next slide, but I'm not really going to talk too much about why and how it's easily broken by water, but just know that ionic bonds can easily be broken down by water. All right, I'll stop for a minute. If you guys have any questions, feel free to ask. I'll let everyone kind of get caught up on note taking for just a few seconds here. Okay, so we've covered covalent bonds, polar and nonpolar. We've got the ionic bonds. Now I want to talk about hydrogen bonds, which are really, really important from a biological perspective. They're actually fairly weak, but they hold a big, a way that they're important in our body is they hold a lot of the proteins together in the correct shape, and they also hold our DNA together in the correct shape. So hydrogen bonds are really important in our biological molecules, which we'll get into later in this chapter. So what is a hydrogen bond? Sometimes they're a little bit difficult for students to understand, so I'll try to break it down as simply as possible here. Okay, so it obviously involves hydrogen, so it's always going to involve a hydrogen atom, and that hydrogen atom is attracted. So let's think about water here. Water is the easiest example. That hydrogen atom in water, so this is H2O, is attracted, so it's slightly positive. It's attracted to the slightly negative oxygen in another water molecule. So this happens between molecules. That's really important. So it's not necessarily creating we're not creating one water molecule here. We already have the water molecules created by the covalent bonds, which you can see. So covalent bonds attach hydrogen to oxygen to make a water molecule. That's a polar covalent bond. So that means oxygen is slightly negatively charged because it holds onto those electrons really tightly. Hydrogen is partially positive because the electrons are being pulled away from it a little bit further. So we have a polar covalent bond here. And because that hydrogen now is slightly positive, and maybe this diagram is a little bit better because it has the charges on here. So here we have the slight positive. I'm going over to the right. Can you give me a thumbs up if you can see my mouse, or a thumbs down if you can't, something, or say yes or no in the chat. I just want to make sure. Okay, good. Thank you, Max. Okay. So the hydrogen atom over here in this water molecule, you can see it's partially positive because of that polar covalent bond. This oxygen in the next water molecule over is partially negative. So that partial positive and partial negative, they're going to be attracted to each other. Whoa. I don't know what I just did. They'll be attracted to each other, which means that those two water molecules are going to be bonded together through a hydrogen bond. So that's what a hydrogen bond is. It's between between molecules that have a polar covalent bond within them. I hope that makes sense. It's really hard to explain in a simple way. But you have a slight positive part of a molecule, you have a slightly negative part of another molecule. Those two are attracted together. Hydrogen is always going to be the partially positive side of the molecule. Okay, so that's a hydrogen bond. You have to have a polar covalent bond within the molecules that are interacting in order for that to happen. All right, on to the weakest. It's really just an attraction. I don't know that it's technically considered a bond. We have something called van der Waals forces. And these are simply sort of brief, weak attractions between different molecules. So this is involved, the whole reason behind why these occur is because these electrons, if you imagine an atom with, the electron cloud around it, electrons are constantly swirling around in this cloud. So sometimes they may be more to the left of the atom. Sometimes the electrons might be shifted more to the right. And remember, those electrons are negatively charged. So they're pulling the negative charge potentially back and forth across the atom, just depending on where they are around that atom. And for our purposes, I'm sure from a physics perspective, there's a way to predict where an electron is, but for our purposes, it's kind of random where those electrons are. So it creates temporary polarity, which means some of the atom, even though overall the atom or the molecule might not be negatively or positively charged long term, it might be positively negatively charged for a very short period, or partially positively charged for a very short period, or one side of it will be. So down here you can see where all the electrons are sort of on one side of the atom, and that is basically what's going to allow for attraction to another atom that may be in the same formation. And then the negative side of that atom will be attracted to the positive side of the other atom. So even when there's no technical polarity, there's still movement of electrons, which is going to create this kind of shifting charge within an atom. That shifting charge will allow for temporary attraction, and then that attraction will break apart as soon as the electrons move around again. So it's kind of this constant attraction and then release of the attraction. So over and over again, many times. And it happens very frequently in many different biological molecules. And I've noted here, in particular, it's really important in protein folding. So I mentioned hydrogen bonds are important in protein folding. Van der Waals forces also are. So it holds these molecules together. Let me know if you guys have any questions about that. Okay. So before we move on to water, I am actually going to have you guys, rather than listen to me for even longer, I'm going to have you guys break into breakout groups. Yeah, close that. So what I want you to do is go to Canvas, and there's a document under the Unit 1 module called Chem Bonds Table, I think is what I labeled it as. So I'll give you guys a second to go there. And you can either, I would say, download it and type into it. It's just a Word document that has these different kinds of chemical bonds. And I will pull it up here as well for you guys to see. So I'm going to put you guys in breakout groups and have you fill out the missing parts of this table. So it's sort of partially filled out. Let me share this with you. Okay, so this is what it should look like when you download it. Chem bond table is what the document is called on Canvas. Let me know if you can't find it, please. So here you can see in the first column, you want to put in the bond types. I've put in polar or covalent first off. So it's missing the other three, and then description. So just a brief description. I would say put the description that I gave you in your own words. That's going to be a lot more helpful than just copying what's on my slides. So try to describe it in a way that makes sense to you. The strength, you know, make your best guess. Well, I guess the other two, yeah, those are pretty straightforward. The two that are missing are pretty straightforward. And then I've given you examples. So just some kind of drawn out examples. If there's something else that's helpful to you, definitely fill that in too. Okay, so that's enough. You guys are going to fill this out. I'm going to put you guys into breakout groups right now. So I'll give you about, let's see, 3 or 4 minutes to kind of get working on that and help each other out. And then we'll come back and continue on our way. So let's see. I'm going to make the breakout rooms like 3 to 4 participants. So here we go. Let me know if you have any questions. I'll be sitting here. Of that info filled out. So I want to look at just a couple of these to make sure you guys were on the right track. So let me share this document so you can see it in front of you. So who wants to tell me what this first row was? What type of bond is this showing? Who wants to offer that up? If you can, oh wait, there's a chat. There we go, hydrogen, nice. Thank you, Kathy. Yep, that is a hydrogen bond. Does anyone want to offer up what description they gave, since mine was long and long-winded? Did anyone come up with a better, like, shorter description? No. Okay, so for the description, hopefully you have something along the lines of a partially positive hydrogen being attracted to a partially negative atom in another molecule. Both are polar covalent bonds within their own molecules. So again, I know it's long-winded, but hopefully you got something along those lines. And then, right, the second was a covalent bond. And what strength is a covalent bond, strong or weak?
They are strong.
Yep, they are very strong. They're going to be the strongest, actually. Very good. Thank you. And then this third row, what did you guys put for that? What kind of bond is that? Yep, ionic. Thank you, Abigail. And so the description, those are pretty strong. The description there would just be a transfer of electrons, right? Of one electron or more between atoms. And then the final row, what kind of bond or attraction is that? Van der Waals, good. You beat me to it, Kathy. Good job. Okay, so if you don't have all that filled out, definitely take the time to do that. That's really just for your benefit to understand and kind of have these bond types. I like having tables so you can just kind of reference stuff really quickly. So that will be helpful for you in studying, just being able to see all of them sort of in one place next to each other and have those examples. Hopefully it's helpful. Okay, thank you guys for participating in that. For those of you who never joined the breakout room, I'm disappointed. Yeah, so when I do breakout rooms, it is helpful if you guys will actually join them. Otherwise, you're just leaving one or two people in a room. So thank you guys for those of you who participated, which was most of you. Okay, let's stop sharing that and move on to talking about water. Let's see here. Okay, so we talked about like the main types of chemical bonds there. Now I'm going to talk a little bit about water and then mixtures that involve water. Water is basically essential to all life on Earth, right? So when NASA goes to explore other planets, they're always looking for water. That's because we have to have water to survive. And water is actually pretty amazing. I'm going to show you this video called Liquid Awesome in just a minute, just talking about the different properties of water. So rather than going into and you hearing me kind of describe each of these main properties of water, I am going to let this video do it for me because it's a little bit more exciting than I could do on a PowerPoint slide. So just to run through the main properties that I want you to be familiar with. The importance of water and the ability of it to support life is due to the fact that it is a universal solvent, so it dissolves a lot of things. Like I said, table salt will dissolve very easily in water. If you ever have a dish and you cook a casserole and everything's kind of stuck in the dish, if you leave it overnight, even if it's hardened into the dish, you leave water in it overnight, it breaks it up. It's pretty amazing. So it's a really good dissolving agent or solvent. It also has what's called cohesion and adhesion. Cohesion is where water will stick to itself. So one water molecule sticks to another water molecule. That's really important. Adhesion is where water will stick to, so water is polar. Definitely make sure you have that. I don't know if I had that on a slide yet. Water is polar. It will stick to or be attracted to other polar substances. That is adhesion. So cohesion, it's attracted to itself. Adhesion, water is attracted to other polar substances. And then thermal stability, that's really important for the survival of life on Earth. So we are made up of like 3/4 water. So that really helps maintain our internal temperature because water can take on a lot of heat or release a lot of heat without actually changing temperature all that much. So it keeps us regulated from a temperature standpoint as well as our climate. So I'm going to try to show this video. Hopefully it comes through. I think I can share it in a way. Hang on. where the volume might come through a little bit better. So let me get this going here. There. Okay, I'm going to share the sound. I think that'll help. Optimize for video clip. Okay, let's see how this works. Okay, here we go.
Delivery, I chose the vegetarian box, and the meals that I received were the salsa verde enchiladas, harissa.
Hello there. Here at Crash Course HQ, we like to start out each day with a nice, healthy dose of water in all its three forms. It is the only substance on all of our planet Earth that occurs naturally in solid, liquid, and gas forms. And to celebrate this magical bond between two hydrogen atoms and one oxygen atom, here today we are going to be celebrating the wonderful life-sustaining properties of water. But we're going to do it slightly more clothed. Much better. When we left off here at the biology crash course, we were talking about life, and the rather important fact that all life as we know it is dependent upon there being water around. Scientists and astronomers are always looking out into the universe, trying to figure out whether there is life elsewhere, because, you know, that is kind of the most important question that we have right now. They're always getting really excited when they find water someplace, particularly liquid water. And this is one reason why I and so many other people geeked out so hard last December when Mars's 7-year-old rover Opportunity found a 20-inch long vein of gypsum that was almost certainly deposited by long-term liquid water on the surface of Mars. And this was probably billions of years ago, and so it's going to be hard to tell whether or not the water that was there resulted in some life, but maybe we can figure that out, and that would be really exciting. But why? Why do we think that water is necessary for life? Why does water on other planets get us so freaking excited? So let's start out by investigating some of the amazing properties of water. In order to do that, we're gonna have to start out with this. The world's most popular molecule, or at least the world's most memorized molecule. We all know about it. Good old H2O. 2 hydrogens, 1 oxygen. The hydrogens each sharing an electron with oxygen in what we call a covalent bond. So as you can see, I've drawn my water molecule in a particular way, and this is actually the way that it appears. It is V-shaped. Because this big ol' oxygen atom is a little bit more greedy for electrons, it has a slight negative charge, whereas this area here with the hydrogen atoms has a slight positive charge. Thanks to this polarity, all water molecules are attracted to one another. So much so that they actually stick together, and these are called hydrogen bonds, and we talked about them last time. But essentially what happens is that the positive pole around those hydrogen atoms bonds to the negative pole around the oxygen atoms of a different water molecule. And so it's a weak bond, but look! They're bonding! Seriously, I cannot overstate the importance of this hydrogen bond. So when your teacher asks you, what's important about water? Start out with the hydrogen bonds, and you should put it in all caps and maybe some sparkles around it. One of the cool properties that results from these hydrogen bonds is a high cohesion for water, which results in high surface tension. Cohesion is the attraction between two like things, like attraction between one molecule of water and another molecule of water. Water has the highest cohesion of any non-metallic liquid, and you can see this if you put some water on some wax paper or some Teflon, or something where the water beads up, like some leaves of plants do it really well. It's quite cool. Since water adheres weakly to the wax paper or to the plant, but strongly to itself, the water molecules are holding those droplets together in a configuration that creates the least amount of surface area. It's this high surface tension that allows some bugs, and even I think one lizard, and also one Jesus, to be able to walk on water. The cohesive force of water does have its limits, of course. There are other substances that water quite likes to stick to. Take glass, for example. This is called adhesion, and the water is spreading out here instead of beating up because the adhesive forces between the water and the glass are stronger than the cohesive forces of the individual water molecules in the bead of water. Adhesion is attraction between two different substances, so in this case, the water molecules and the glass molecules. These properties lead to one of my favorite things about water, the fact that it can defy gravity. That really cool thing that just happened is called capillary action. And explaining it can be easily done with what we now know about cohesion and adhesion. Thanks to adhesion, the water molecules are attracted to the molecules in the straw. But as the water molecules adhere to the straw, other molecules are drawn in by cohesion, following those fellow water molecules. Thank you, cohesion. The surface tension created here causes the water to climb up the straw. And it will continue to climb until eventually gravity, pulling down on the weight of the water in the straw, overpowers the surface tension. The fact that water is a polar molecule also makes it really good at dissolving things, which we call it's a good solvent then. Scratch that. Water isn't a good solvent. It's an amazing solvent. There are more substances that can be dissolved in water than in any other liquid on Earth. And yes, that includes the strongest acid that we have ever created. These substances that dissolve in water, sugar or salt being ones that we're familiar with, are called hydrophilic. And they are hydrophilic because they are polar. And their polarity is stronger than the cohesive forces of the water. So when you get one of these polar substances in water, it's strong enough that it breaks all the little cohesive forces, all those little hydrogen bonds, and instead of hydrogen bonding to each other, the water will hydrogen bond around these polar substances. Table salt is ionic, and right now it's being separated into ions as the poles of our water molecules interact with it. But what happens when there is a molecule that cannot break the cohesive forces of water? It can't penetrate and come into it. Basically, what happens when that substance can't overcome the strong cohesive forces of water and can't get inside of the water? That's when we get what we call a hydrophobic substance, or something that is fearful of water. These molecules lack charged poles. They are non-polar and are not dissolving in water because, essentially, they're being pushed out of the water by water's cohesive forces. Water, we may call it the universal solvent, but that does not mean that it dissolves everything. There have been a lot of eccentric scientists throughout history, but all this talk about water got me thinking about perhaps the most eccentric of the eccentrics, a man named Henry Cavendish. He communicated with his female servants only via notes and added a staircase to the back of his house to avoid contact with his housekeeper. Some believe he may have suffered from a form of autism, but just about everyone will admit that he was a scientific genius. He's best remembered as the first person to recognize hydrogen gas as a distinct substance and to determine the composition of water. In the 1700s, most people thought that water itself was an element, but Cavendish observed that hydrogen, which he called inflammable air, reacted with oxygen, known then by the awesome name deflostigated air, to form water. Cavendish didn't totally understand what he'd discovered here, in part because he didn't believe in chemical compounds. He explained his experiments with hydrogen in terms of a fire-like element called phlogiston. Nevertheless, his experiments were groundbreaking, like his work in determining the specific gravity, basically the comparative density of hydrogen and other gases with reference to common air. It's especially impressive when you consider the crude instruments he was working with. This, for example, is what he made his hydrogen gas with. He went on not only to establish an accurate composition of the atmosphere, but also discovered the density of the Earth. Not bad for a guy who was so painfully shy that the only existing portrait of him was sketched without his knowledge. But for all of his decades of experiments, Cavendish only published about 20 papers. In the years after his death, researchers figured out that Cavendish had actually prediscovered Richter's law, Ohm's law, Coulomb's law, several other laws. That's a lot of freaking laws. And if he had gotten credit for them all, we would have had to deal with like Cavendish's 8th law and Cavendish's 4th law. So I, for one, am glad that he didn't actually get credit. We're gonna do some pretty amazing science right now. You guys are not gonna believe this. Okay, you ready? It floats! Yeah, I know you're not surprised by this, but you should be, because everything else, when it's solid, is much more dense than when it's liquid, just like gases are much less dense than liquids are. But that simple characteristic of water, that its solid form floats, is one of the reasons why life on this planet, as we know it, is possible. And why is it that solid water is less dense than liquid water, while everything else is the exact opposite of that? Well, you can thank your hydrogen bonds once again. So at around 32 degrees Fahrenheit, or 0 degrees Celsius if you're a scientist or from a part of the world where things make sense, water molecules start to solidify, and the hydrogen bonds in those water molecules form crystalline structures that space molecules apart more evenly, in turn making frozen water less dense than its liquid form. So in almost every circumstance, floating water ice is a really good thing. If ice were denser than water, it would freeze and then sink, and then freeze and then sink, and then freeze and then sink. So just trust me on this one. You don't want to live on a world where ice sinks. Not only would it totally wreak havoc on aquatic ecosystems, which are basically how life formed on the Earth in the first place, it would also, you know, all the ice in the North Pole would sink, and then all of the water everywhere else would rise, and we wouldn't have any land. That would be annoying. There's one more amazing property of water that I'm forgetting. Why is it so hot in here? Heat capacity. Yes, water has a very high heat capacity, and probably that means nothing to you, but basically it means that water is really good at holding on to heat, which is why we like to put hot water bottles in our bed and cuddle with them when we're lonely. But aside from artificially warming your bed, it's also very important that it's hard to heat up and cool down oceans significantly. They become giant heat sinks that regulate the temperature and the climate of our planet. Which is why, for example, it's so much nicer in Los Angeles, where the ocean is constantly keeping the temperatures the same, than it is in, say, Nebraska. On a smaller scale, we can see water's high heat capacity really easily and visually by putting a pot with no water in it on a stove and seeing how badly that goes. But then you put a little bit of water in it, and it takes forever to freaking boil. Oh, and if you haven't already noticed this, when water evaporates from your skin, it cools you down. Now, that's the...
All right, we are going to stop there. Sorry, that went up to kind of the last minute. But we'll pick up with more water and then get into biological macromolecules on Monday. Like I said, I'll email you guys what we're doing for meeting on Monday. And let me know if you have any questions about either of the assignments that are due by Monday. Have a good weekend.